So I've got this PacSci Reslver motor here, Pacific Scientific. On the back shaft there's a resolver. I've got it wired first to older Zenith with the 8367 DSP and the resolver input. I've got it wired up from documentation from the Pacific Scientific driver. I can decode the colors pretty easy. So what I'm going to do first is get the system up and running, show how to load the data, find the motor data to replace the PacSci. And then after I get this up and running, I'm going to use this CSR adapter to adapt to the new Rev2 Zenith, which has clock and data to read serial, takes the resolver, converts to serial clock and data. So we can use one drive to do resolver or incremental with the adapter. And we'll first start off by looking at the plate data on the motor here. So on the side of the motor is a metal plate with the numbers carved into it, and it's a R43 HS or H winding, and it has these specifications. These are pretty sufficient, but I did find the data for the motor. I'm going to take a quick look at the old PacSci SCE900, which was used to drive this motor in the past, maybe 20 years ago, 15 years ago. It's a pretty good driver system for resolver, but the important thing I'm going to key in on is the wiring diagram that shows the sine and the cosine and the excitation and the motor power wires and the shield. Notice the shield is connected to the drive, not the motor case, and individually shielded twisted pairs. And the color code took a little bit of figuring out, but we have the color code here. So the blue and the black was the sine, the black and the red was the cosine, and the black and the white was the excitation, and the shield connecting to frame ground on pin 1, and there's a motor temperature sensor. Connect that to input. It's a positive temperature coefficient, so when it gets hot, the resistance goes up and it switches off to protect the motor. But the drive has I2T limiting, so that should be fine. So I'm going to use this on the old XTL Rev0, and then I'm going to convert this over to the new Rev2 using the Copley serial resolver adapter. I'll just unplug from the drive and plug into one end of the cable, which goes through the adapter and then plugs into the new drive. Just to give us a brief on the drive, this is the old Rev0 Zenith. It had a -R option, and this is the new Rev2, which takes the CSR in. And again, the CSR is just a little adapter with some cables to convert resolver to clock and data. It actually performs better as far as like the signal to noise ratio. There's no PWM amplifier on it, so yeah, that's pretty good. So how we start off here, originally we get the data for the motor, and you can look up the R43, and then you can get all the specifications of the motor. Here's the H winding and the resistance, inductance, and whatnot. And so in CME, in the old drive, I'd configure it as a resolver, and 16,384 counts per rev is kind of typical. If you had a break, you put some break times in there. Good. And then the motor data, 6-pole motor, and just fill in all the data from the data sheet. Hit calculate, and this calculates the initial tuning parameters. Because I'm actually connected to a drive, I can get initial tuning parameters and current limits. The motor is in amps RMS, so this is amps peak. So this This drive is pretty good for, there's some tuning values for the velocity loop. You can increase this velocity. It's got a high back EMF, so you might not be able to hit that speed unless you got 240. Yeah, there's a warning here about, be careful, you only got 120 volts AC hooked up. And then if you had a large inertia, maybe you knock this proportional gain down and dial back a little bit on the integral. I think the file we can save, so to transport over from an old drive to a Rev 2, we just save the CCX file. I've got a PacSci, so I'll just save it. Yeah, overwrite it. And then what I'm going to do is connect over to the new drive. So, a good idea to hot swap. As you can see, unplug this and plug that in. Okay, so that's pretty easy. And AC power. Actually, we don't even need AC power to do this. We're just going to hook up the new drive and talk to it over the serial port with my SCR USB RJ11 serial adapter. Turn the power on, connect to the drive, and then when CME loads, we can load the new file, restore, CCX file, and just go find that file. So CME version 8.1, I'm using the beta 24. This allows us just to open up a file from a slightly divergent drive. And let's just check it. Yeah, see, Copley serial resolver, same counts per rev. If you had a multi-speed resolver, you can do that. Like a 6-pole motor might have a 3-speed resolver. That's 3 times that per rev. Anyways, I just opened the file and I'm just taking a look at it, make sure it looks right. Yeah, so all the parameters came in, and the current loop's the same, the velocity loop. I've noticed a little higher gain in some systems, so we may tune it down a little bit, the velocity and position loop, but otherwise, pretty much just drop in the old file. And then after you open the file, you got to hit save to flash. And that way you can then, run and tune as normal. Probably just, run the system and not even notice a difference. I had a little challenge with this resolver, so I'm going to go through some notes here about a resolver. So there's the R1 and R2, which is the excitation of the stator, and then the rotor will rotate. You'll get your sine and cosine. These are 90 degrees apart, so you'll get sine on one and cosine on the other. It's principle of mutual inductance, but you can tell if there's a problem with your resolver, the ohms don't work out. So if you measure this, it's like 100 ohms, and if you measure these two, it should be like 30 ohms. So we've got some stator supposed to be 85 ohms, and both rotors, sine and cosine, is supposed to be 31 ohms. So you can use an ohm meter to measure that. I've got it all wired up and the data entered. And I'm turning the shaft of the motor with the resolver drive, and I see the cosine, but I don't see the sine. The sine's like a flat line. So I see the excitations working. There's the modulation, and we'll demodulate it in the drive. So the cosine's good. The sine is not good. I took some measurements. I measured 150 ohms on the rotor. I got 30 ohms for the cosine, but I don't have 30 ohms for the sine. It's 100 ohms. Therefore, I've got a bad motor. So it's a little bit of a challenge to try to tune this thing. Under voltage is a fault, and the counts kind of don't really add up very good. when I turn the shaft, I should see a normal count. So this is the effect of a bad sine or cosine. Voltage, sine, and voltage, cosine, and hit record, waiting for trigger. Let's just trigger immediate. Yeah, not function generator, but trigger immediate, hit record. And it's collecting some data as I turn the shaft of the motor. And no voltages for sine and cosine, but because there isn't, it goes through the adapter. But you do see that there's a feedback error, and so we can take a look at the latch fault feedback error. So there's a problem with feedback. I guess you could say it could be a problem with CSR, but let's ring out the feedback cable and see what the problem is. And we can use our ohm meter. So just measuring down the motor here. We've got the resistance of a pair of wires right through the cable here. Yeah, there's the 30 ohms. What? 100 ohms should be 30 ohms. And then here's the excitation coil, 150. So conclusion is that, this motor has a resolver problem. But I wanted to show how easy it is to transfer over from an older, obsolete 8367 to the new ARM drive. So